So you remember in the previous recitation class, we were finding the electric field created by an infinitely long, uniformly charged cylinder of radius r capital, and volume charge density is given. And since ρ is constant, it means that cylinder is uniformly charged, right? And we assumed it's positively charged. So part A we solved. We found the expression for the electric field outside of this cylinder. Now, part B, let's find the electric field inside of the cylinder, right? And again, using Gauss's law, right? So, since we're planning to use Gauss's law, you remember the first step that we have to make. We have to pick a Gaussian surface. Any Gaussian surface will work, but we need to pick the best surface so that we can solve problem with the least amount of efforts. And of course, after the previous class, you should be able now to guess easily which Gaussian surface will be the best one. Small cylinder of finite length positioned inside of our physical cylinder. Again, I'm using my can of salt, right? Readily available here. Right, okay, I will use solid lines. Wrong color. I usually use green all the time for the Gaussian surface. So that's my Gaussian surface, right? So let me say this is a Gaussian surface of some finite length L. Again, L is not given, but you remember, like in part A, at the very end, it will just disappear. Right. Okay, so now, of course, according to the logic, at least my logic, it's better to first find the electric flux. And the thing is, guys, steps that you have to make in order to evaluate this integral are exactly the same as steps we've made in part A. Exactly the same. Not a single symbol is going to be different. Again, you're going to split this Gaussian surface into 3 surfaces, right? So you can call this as S1. For example, this as S2. This will be your S3. Again, you will take some small patch, right? So this will be area vector. Here will be area vector, right? dA. Here again area vector dA that way. Then electric field still the same as the same radial direction. So it means that over here the electric field that way, over here it will be perpendicular to the area vector, here also perpendicular, right? So not a single symbol is going to be different, exactly the same. So as a result, it makes sense. Over here I will just write exactly the same steps, and I will just write the final result. You can just rewrite from your part A from the previous recitation class notes, right? Exactly the same steps, right? Okay, and you can look in your notes, and I think I remember the expression for the electric flux. It's the electric field times the area of this cylindrical wall, S1, all right? So which is 2 pi r circumference, r small, yes, cylinder of radius r small, of course. Right. N times the length. You remember how can we find the area of the cylinder? Circumference of the base times the height or the length of the cylinder. So it will be 2 pi r times L. Okay, so that's the flux. And according to the Gauss's law, it should be equal to Q enclosed over epsilon naught. So that's what we have now. And now the question is about the total amount of charge inside of our chosen Gaussian surface. and as I keep saying to you, every time it's about definition of, in this case, volume charge density, because that's what is given. So by definition, it's a Q divided by V, right? So let me frame it sort of like this. And everything comes from here. all this software is making noises, right? All right, so look, it's a charge, whatever charge you want to use, divided by the volume over which this charge is distributed. So now I'm suggesting let's use this formula for Q enclosed. But first of all, we need to see on the picture where Q enclosed is. Again, by definition, you remember it's the total amount of charge physically present inside of your Gaussian surface. Inside of your Gaussian surface, this is Gaussian surface. Inside, it means that it's over here. So that's where our Q enclosed is. See that again, it's just meaning is quite trivial. So you just need to count all the charges physically embraced by your Gaussian surface. That's what we have here, right? So, and now I'm suggesting let's use this formula for Q enclosed. So over here upstairs it will be Q enclosed divided by what? By the volume over which Q enclosed is distributed. It's this volume of the Gaussian surface. Let me label like V sub r small. Basically, it means the volume of the cylinder with the radius r small. So, and we're interested in actually in the charge, so I can write Q enclosed equals rho times the volume of our Gaussian surface. Everything comes from this formula, right? Because rho is given, we don't need to find rho. In the previous lecture yesterday, we actually had to find the volume charge density of the sphere, but because in that problem density was not given, but here density is actually given, so we don't need to find that, right? Because quite often on the exam in the on an exam in the past, if I give a problem like this, maybe like 25-30% of students at the end still try to find rho. No, rho is given from the very beginning, right? So over here I can write, so Q enclosed equals to rho times volume of the Gaussian surface. So it will be volume of the Gaussian surface. It's a volume of the cylinder. Of course, everyone who is in this class, of course, knows how to find it, right? So you take the base, pi r squared, r small, because we are using the volume of the Gaussian surface, right? Pi r squared times length, volume of the cylinder. So it's a rho times pi r small squared times L, right? So that's the expression for the enclosed charge, enclosed by our Gaussian surface. Okay, so now almost final step. So now we just need to plug it into the previous expression. And let me rewrite that expression over here, finalizing the this problem. So E times 2 pi r times L equals to Q enclosed, this Q enclosed, rho pi r squared times L divided by epsilon naught. So now let's simplify it. L can be cancelled, then pi can be cancelled, and r, here and r. So one r can be cancelled. So here we'll have r to the power of 1, with the power of 1. So, as a result, E as a function of r can be written. This factor of 2 will go downstairs in the denominator. So it will be rho times r divided by 2 times epsilon naught. So that's the expression. Okay, actually, function. It's a function for the electric field inside of the our cylinder. And again, remind you that this is for r small less or equal than r capital. Right. So these are constant. So this is the constant, and r is the variable. So pretty much electric field is growing which way? Linearly. It's basically like y equals 5 times x. y equals 5 times x, it's a straight line, right? So here we have constant times r. It's a straight line. Okay, make sense? This time I move, of course, much faster relative to the previous recitation class because very similar idea to part A. So now let me plot this function and the function from part. Yeah. Just somebody unmute unmuted. Okay, so part A. For part A, the answer was, let me just rewrite. Electric field was equal to rho r squared over 2 epsilon naught and 1 over r. So that was for part A. So this is part B. Right? And now I just want to plot this and this on the same graph because it's quite useful once you find electric field everywhere. It's good to plot to see the whole picture. So R, this is electric field, magnitude of the electric field. Let's say this is the surface of the cylinder R. And inside, this is inside, when R smaller than R capital. So I'm talking about this region, right? So that's where this function works. And it's a straight line, right? Because E is proportional to the R. So straight line. Then outside, when R larger than R capital, this region, right, from here to infinity, it decays as 1 over R. Again, this is just a bunch of constants. So, and of course, these two functions must meet at the boundary, at the border. So here it's a proportional to 1 over R, here proportional to R. Okay, so that's how it is done. And it's not trivial, but at the same time it's not rocket science, right? After a couple of examples, right, you should be able to feel comfortable. At least I remember myself in your shoes, right, being you undergrad students. We actually like the problems like this. They are well structured. Logic is not ridiculously complicated. So, and after practicing a couple of times, it was like that, right? Now, in order to prepare you for the homework, because this problem 2450 is in your homework, right? And the only difference in your homework, not rho is given, not volume charge density, but the linear charge density is given. So the same problem, but you need to solve it with linear charge density. So let me connect or show you the transition between these two charge densities, linear and volume charge densities, right? And you shouldn't be surprised at how come that the same problem is stated using two different charge density. For example, I can easily introduce, let's say I have the same object, right? I know, can full of salt, right? And of course, I can describe that salt using volume charge density. If I take the total mass of the salt, if I divide that by the volume of the cylinder, of course, I will get volume charge density. But at the same time, for whatever reasons, I might want to describe it using linear charge density. For that case, I need to take, again, total mass, but now I will divide it not by the volume, but by the length. And I will get, I don't know, 5 kilograms per meters, for example, right? Instead of 5 kilograms per cubic meters, I will get 5 kilograms per meters, right? Let's say for my descriptions, that I think will be more convenient. So the same story here. Right? Sometimes linear charge density can be maybe more useful, right? So how can we make a transition between these two charge densities? So pretty much problem is solved. This problem is solved. So let me put a new bullet, right, and write homework help. Right. Um, okay, it's a 42450. 2450 problem. So, linear charge density. Lambda. Units of lambda. Oh, brackets are ugly. Right. Units of lambda. As I told you, in order to find linear charge density, you take total charge, and now you need to divide it by the length. Again, you remember that second lecture, that slide about all possible charge densities. It's all from there. It's all from there. So units are coulombs divided by meters. Volume charge density. What are the units? As I told you, okay, like here, it's a charge divided by the volume. So it's a coulombs divided by meters to the power of 3. So now question is, how can we make a transition from lambda, no, from rho to lambda? How can we make a transition between these two densities? Right. Okay, so in order to connect them in this problem, let's use part A, results of part A, uh, results for Q enclosed, for enclosed charge. All right, so let me use Q enclosed from part A. So let me recall. You can look at your notes, right? I think I remember. So in part A, we took volume charge density and multiplied by the volume, this volume, pi r squared times L. Again, you can look at your notes, right? So that's how we can write Q enclosed using rho. How can we write the same Q enclosed, but now using linear charge density? That's why I wrote units. Look, linear charge density, coulombs divided by meters. And again, it's we discussed that in that slide in the second or third lecture, right? So in order to get charge again, because that's what we're trying to find, charge. In order to get charge, we need to multiply linear charge density by length, so that these meters can be canceled, and we will get units of charge. Length of our Gaussian surface, which we introduced in part A. So you take just lambda and multiply it by the length of our Gaussian surface. So you see, that will be Q enclosed in your homework problem of part A of your homework problem. You see, it's easier than this, right? But for part B, actually, volume charge density is easier to relate, at least in my opinion. So, but anyway, this part of this equation gives us a relationship between these two densities. Look, if we now L on both sides, we can cancel it and we can connect lambda and rho. Solve it for rho equals lambda divided by pi r squared. Rho equals lambda divided by pi r squared. So now, if you know this, you can use these results and rewrite it in terms of lambda. So, for example, this Q enclosed, here Q enclosed, take this rho, plug it over here, and you will get Q enclosed in terms of linear charge density. And the same with part A, but in part A, we already wrote down. It's a lambda times L. So this should help you with the homework, with this problem in your homework, right? And next week I will give you a take-home quiz about these charge densities, linear volume charge densities, because it's a very simple idea, right? And don't argue that it's a complicated idea. No, it's one of the simplest in physics, engineering, of course. And you must be very, very comfortable. And so far I noticed that students are kind of not comfortable. Sometimes even just panic about this when we start using these densities, although it shouldn't be like this, right? So I will give you the quiz, and then of course you can ask us for help, right, if something is not clear, right? But you need to struggle through that in order to be comfortable at the very end. Right? But of course I will announce that later, right, about the take-home quiz, next one. So any questions about this? Otherwise we will move to properties of conductors, which we started discussing in the yesterday in the lecture. Okay. I think I told you, right? So upload quiz 2 to Gradescope, and I think deadline I set is 1 p.m., right? 1 p.m. today. So we discussed these properties of conductors. Okay, we started discussing them in the lecture, but we haven't finished. So as a result, I had to add 3 additional properties of conductors. So first of all, in this course, we're going to mention only 2 types of materials, dielectrics and metals, or conductors. What is the major difference between them? Of course, there are tons of differences between them. It's almost like comparing apples and oranges. Okay, not completely. Probably I shouldn't be using that comparison. All right, so the major difference, any material consists of a bunch of atoms, okay, not bunch, of gazillion number of atoms, right, almost like a crystalline structure. And between those atoms, there are actually gigantic spaces, right, gigantic relative to the sizes of atoms. And in metals, in conductors, all that space between atoms is actually filled with free electrons. There used to be valence electrons belonging to a certain atoms, but if you increase the temperature, for example, of the conductor, some additional valence electrons will get loose, and they will become also free electrons. So in conductors, all that empty space is filled with gazillion number of free electrons, which are free to move anywhere they want. But in dielectric materials, all that space between atoms are actually empty. There's nothing over there. So all electrons are staying with their families, right, in the atoms, right? So there's an atom, inside there is a nucleus, right? And then around that nucleus there are electrons orbiting, and they are all together. Electrons, they don't leave that their families, right? So they're atoms. As a result, all that space between atoms is actually empty. But in the conductor, all that space is filled with free electrons. So that's the major difference. And then the rest kind of follows from that. So item number 1, properties of conductors. They have conductors. That's what I mean. Have tons of free electrons. Then over here, I added electrostatic equilibrium. We need to refresh that. We discussed it yesterday in the lecture, but anyway, I need to say a few words about that one more time. So let's say you have some piece of metal, and let's say you expose that piece of metal to some external electric field, whatever electric field, whatever piece of a conductor, and once you expose that conductor to the electric field, inside of the conductor there are tons of free electrons. Of course, those electrons will start filling the electric field. And of course, they will start experiencing electric force from that electric field. And of course, that electric force will start driving those electrons crazy, right? And of course, so they experience the force, and of course, they will start running. And those electrons will keep running and running and running for some short period of time, right? Until they will make net electric field inside of the conductor 0. Otherwise, they will never stop running, because otherwise they will feel electric field, or not electric force. So they will keep running and running and running until the net electric field inside of the conductor will be 0. So it means what? It means that they distribute themselves somehow in the conductor. They will create additional internal electric field inside of the conductor, and that electric field is opposite relative to the direction of the external electric field. As a result, you have two electric fields, one external, one is internal because of the distribution of electrons, and these two electric fields give us 0 net electric field. So at that moment, electric field, net electric field 0, electrons will stop feeling any force, they will stop running. So, and after that, we can say that the conductor is in the electrostatic equilibrium. Electric field is 0 inside, and the electrons no longer move. All right. So they get settled, buy house, I don't get married, and live happily ever after. Right. So they get settled. So that's what happens at the in the conductor at the state of electrostatic equilibrium. Right. Okay, so now immediately we get to the second item. Electric field inside of the conductor in the electrostatic equilibrium is 0 all the time. But of course, you need to wait for a short period of time until electrons will finish doing their job, right? Making electric field 0, and they get settled. So now, next, okay, let me just draw maybe a piece of a conductor. So this is piece of a conductor. Okay, metal. And as we just wrote, so discussed electric field equals to 0. All right, and then what about excess charge? Again, we discussed that yesterday in the lecture. What if you dump some amount of charge on the conductor? And of course, the logical question, where is this charge, excess charge, going to reside? Inside, or maybe on the surface, or who knows, right? And yesterday we proved in the lecture, using Gauss's law, that it's impossible for an excess charge to be inside of the conductor. Again, in the electrostatic equilibrium, every time we assume that state, we wait for a short period of time for the electrostatic equilibrium, and then we discuss all these properties. So excess charge cannot be inside of the conductor, so it can be only on the surface of the conductor. Excess charge can be only on the surface of the conductor. Okay, so let's assume that this piece of metal is positively charged, and I will draw a bunch of these pluses near the surface, right? Only on the surface. It's impossible for excess charge to be inside of the conductor. We just need to remember all these things, because we're justifying them, proving them, but of course at the end of the day you just need to remember. All right, plus most of the engineers, right, they use conductors, right, in the circuits and so on, right? So it's it's quite useful, this fact. Now, that's where we stopped yesterday in the lecture, and now additional pieces of information. All right, so number 4. So all these properties of conductors, it's all about electric field, charge, electric field, right? So we discussed almost everything about electric field in charge inside of the conductor. But what about outside electric field? Electric field just outside of the conductor. Yesterday we will prove it, but for now I will just state electric field inside of the conductor, just outside of the surface of the conductor, is perpendicular to the surface. We will prove it tomorrow. So electric field outside of the conductor is perpendicular. Right, so that's E, right? And you're going to see that experimentally in your lab number 2. You're going to map electric field, and there will be some electrode in your system, and you will see that electric field lines all the time, give or take, almost perpendicular to that electrode. If they're not really perpendicular, that there's something wrong with you, something fishy with the way you are measuring the electric field in your setup, right? You will see it experimentally in the second lab. Now, yes, so we need to write that down. So electric field, which way I wrote? Okay, I see. E outside is perpendicular to the surface. Right. And also, it can be shown mathematically that expression for the electric field outside can be written as eta over epsilon naught. Eta, it's a surface charge density on the conductor, on the surface of the conductor, because we saw charge can be only on the surface of the conductor, so of course it makes sense to introduce this surface charge density, eta. In your homework, I think there is one problem. There is some coin, I know, penny, and you need to find, I think, surface charge density. Electric field just above the penny is given, and you need to find surface charge density. Piece of cake, just solve it for eta, right? So, and you will get the answer. Right. Then, what's next? Yes. So now number 5. Yeah. So now we discussed almost everything. So now next, let's try to make our system slightly more complicated. How? What if I drill, for example, a hole inside of the conductor, basically a void, and that hole basically doesn't have any connection with the outside world. So it's really, really inside, void inside of the conductor. Right. Well, let's say this is my piece of a conductor, and this is a hole. And this is material, again, metal. And again, we assume it is in the electrostatic equilibrium every time. So now the question is, over here, when we were discussing positions of this excess charge, and at this level, at this point, we had only one surface, external surface. But now we created internal surface. So now we have two types of surfaces, and of course, logical question, what about excess charge? Now, is it possible for an excess charge to be on the interior surface? Absolutely logical question. We introduce a surface of a different type, and now we need to check, are we going to get any excess charge on the interior surface? And so let me raise this question. Are there any excess charge on the, okay, let me write it here. I thought saving some space, on the inner surface? Over there, on the inner surface. Absolutely logical question. And in order to answer that question, we need to use Gauss's law. As at the beginning of the previous lecture, I told you, right? So that Gauss's law will be used a lot. So Gauss's law, and you remember, like here, what should be the first step in order to apply Gauss's law? We need to pick We need to pick a Gaussian surface. And you remember, we have a freedom to choose any Gaussian surface we want. It's a universal law, right? So at this point, and we can use any surface. And at this point, I can say, my soul deeply desires, to pick this particular surface just above this surface, this inner surface, interior surface. Again, since I have a freedom to pick any surface, why not? I can pick this one. Right. So this will be my Gaussian surface. There's nothing wrong with this surface. And now, guys, you should be able to tell me what will be the value of this integral. Since this is our Gaussian surface, right? It's just above the interior surface, but it's actually inside of the conducting material, the surface inside of the conducting material, right? This Gaussian surface. Inside of the conductor, the electric field is 0. So we're integrating zero function. So electric field, again, we assume that conductor is already in the electrostatic equilibrium, right? So let me write that down over here. E equals to 0. So this is 0. And as a result, Q enclosed is 0. So it means that Q enclosed to 0, so there is no any excess charge inside of our Gaussian surface. So it means that it's impossible for an excess charge to be on the inner surface in this case. So no excess charge on the inner surface. Okay, so that's item 5, no excess charge. All right, so now the last one. Now let's make the situation is even slightly more complicated. So how can we do that? Let's dump some point charge in our hole. Why not? Situations are possible, yeah. So let's see what are we going to get again in terms of charges on the surfaces, right? So now number 6. Now let me write QH is in the hole. H stands for hole, right? So subscript H I added. So now let me try to reproduce the same picture. No, it didn't work. Right. So that's my hole. Right. So that's the material. Right. And our charge QH. Right. And the same question, are there any excess charge? You know what, I don't want to rewrite that question one more time because to save space, I will just, all right, show with the line. So it's exactly the same question we are asking over here, but situation is slightly different. What if there is a small charge inside of that hole, right? And you should be able to guess immediately which law we're going to use to answer this question. Again, Gauss's law. Gauss's law. Right, so it will be, again, integral of the E dot dA equals to Q enclosed over epsilon naught. And again, since we have freedom to pick any Gaussian surface, I'm saying I want to pick the Gaussian surface which is just above that interior surface. Nothing wrong with that. So that's my Gaussian surface again. Let me emphasize, so that also Gaussian surface. And And I was ready to ask you the same question. What can you say about the electric flux through this Gaussian surface? And after this discussion, everyone should be able to answer immediately, right? So again, since the surface is inside of the conductor, conductor is in the electrostatic equilibrium, electric field inside is 0. So we're integrating a 0 function. Of course, the flux will be 0. So it means that Q enclosed equals to 0. But the difference between this situation and this situation, that right now we know that there is a non-zero charge inside of our Gaussian surface. This is our Gaussian surface, and we can see immediately that there is a QH inside. But the total charge Q enclosed must be 0. So it means what? It means that there must be somewhere else inside of the Gaussian surface the charge with the charge minus QH. So that QH plus minus QH, you're going to get 0 because the total charge inside of the Gaussian sphere, not sphere, surface, must be equal to 0. And where can that charge be? There is only one spot. Inside of the hole, we have only one charge. There is nothing else, right? So it means that on this inner surface, now there will be a charge opposite in sign to this one, but exactly the same in absolute value. So now let me write that down. So Q enclosed, which is 0. And now let's count all those charges. So QH, we see QH, and plus, it looks like now we can have some amount of charge on the inner surface. in order to make Q in 0. So this is given. This we know it's 0. So let's just solve it for Q inner. It will be equal to minus the amount of charge inside of the hole, inside of our hole. So let me frame it. All right. And so from now on, we need to remember that if you have a hole in the conductor and inside of the conductor there is a charge, then this charge is going to induce charges of opposite sign on the inner surface. In simple words, using simple conceptual discussion, all right, we can say this. Let's say this QH is positive. So it's a positive charge. Then this is the conductor full of free electrons. So of course those electrons, they see positive charge inside. And of course you remember opposite charges, they attract. It means that electrons will run to meet this positive charge because they attracted. But over here there is a wall on the border, right? Hot subject these days on the news, right? So here there is a wall. And of course these electrons, they cannot cross this wall, right? So they will be accumulated on this inner surface. And this process is called, we induced negative charge on the inner surface. Negative charge was induced was induced on the inner surface. Or we can justify it like this. So this positive charge creates an electric field everywhere, of course, and of course inside of the conductor. Those electrons, like brave soldiers, they feel, oh my God, there is an electric field inside of the conductor. We need to do something to make it 0. Of course, they will start running, and they will run in such a way so that they will be accumulated on this inner surface. Positive charges will be left behind on the outer surface. They will create those minuses, and these pluses they will create their own internal electric field. And as a result, we will have 2 electric fields, one with this direction, the other one with the opposite direction, internal and external, and they're going to give us overall net 0 net electric field inside of the conductor. Right, so there are different ways of justifying it. But we just need to remember that exactly the same amount of charge, but with the opposite sign, is going to be induced on the inner surface of the hole in this case. But if inside of the hole there is nothing, no charges on the inner surface. Right. Okay, so we're going to solve problem about this, and then quite often on the exam I give questions related to that. Okay, probably I should also mention that over here again electric field is 0, right? Okay, so now let's solve a problem. What's the number? I forgot. 35, I think. Yeah, 2435. So there is a conductor, piece of metal. Okay, let me draw it like this. So that is my piece of metal, and there is a hole. Right. So this is the conductor. Right. So then, let's assume that this piece of a conductor is charged, negatively charged. So I can write Q total equals to minus 50 nanocoulombs. So that's the amount of charge we dumped on the conductor, in the conductor. All right, then it's not the whole story. Now let's position in the hole charge QH equals to plus 100 nanocoulombs. Sort of, I'm trying to dance around item 6. And so now we need to answer 2 simple questions. What's the amount of charge on the inner surface. And we also need to answer the question, what's the amount of charge on the outer surface? Okay, inner surface, it's over there. Outer surface is over here. Okay, so after this discussion, we should be able to answer. So first of all, inner surface, you should be able to answer immediately. So what's the amount of charge on the inner surface? Q inner. Okay, I will drop surface just to simplify my annotations. It's exactly the same as the charge inside in absolute value, but with the opposite sign. Since inside of the hole we have a positive charge plus 100 nanocoulombs, it means that over here on the inner surface there will be negative charge induced, minus 100 nanocoulombs. So the same in absolute value, opposite in sign. Right? So over here there will be a negative charge. So it will be minus equals to minus QH equals to minus 100 nanocoulombs, right? So we just need to remember. But of course, this is the proof using Gauss's law, right? But usually on the exam, on the test, if you just write down, use this factor, I usually buy it, right? So exactly the same amount of charge is induced. Of course, distribution will be complicated of these charges. We're not going to discuss distribution, right? It depends how you position the charge, what's the shape of the hole, right? That's complicated. No, but the total amount of charge will be the same. Now, outer, Q outer surface. Okay, this is slightly more complicated, but once you get the idea, it's also like that. Look, guys, let me ask you this thing. Let's use this comparison in everyday life. Let's assume that we have two rooms isolated from the rest of the world. And these two rooms are connected. And let's say we, I don't know, dump, I don't know, not 10 people into these two rooms. And so we know the total number of people in the two rooms. Now, if I know that there are 3 people in one room, and of course, if I ask you what's the number of people in the second room, of course, it is an insulting question. Of course, 7, right? So 3 plus 7, 10. If I know that 4 people in one room, then there will be second in the second room because the system is closed, and we can use what we can call, I don't know, conservation of people in these two rooms. What I just discussed with you is exactly the same like what we have here to answer this question. No more complicated, not as slightly, not even slightly complicated, more complicated. Look, Q total, it's the total amount of charge inside of our metal, inside of the metal. This QH is not part of the metal. So this QH is not part of this minus 50 nanocoulombs, right? You see that because it's in a vacuum, it's outside of the conducting material. So, and then this Q total, we know it can be where? It cannot be inside of the conductor. We discussed in yesterday lecture. Excess charge cannot be, just let me hold you guys for 2 minutes, sorry, 2 minutes. It cannot be inside of the conductor. It can be only, like we just discussed, on the outer surface or inner surface. There are only 2 places, 2 rooms. So this is 10 people. If we compare with our situation, this is room number 1, this is room number 2. Internal surface, internal, external surface. You see, it's exactly the same situation. So these minus 50 nanocoulombs must be distributed. Some of that will be here, some of that will be there. Q outer plus Q inner must give us the total amount of charge that we dumped inside of the conductor. You see? And of course, we have a fancy name for what I just what I'm trying to apply: conservation of charge inside of the conductor. Again, we assume that charges cannot leak from the conductor. Okay, so let me write conservation of charge inside of our conducting material. Again, this QH is not part of the conducting material. It's in the hole, but it's not part of the conductor. So that's why I'm not counting that. Right? Conservation of charge. So I can write, so Q total equals to Q inner plus Q outer. Okay, we're almost done. So this is given. This we found, and that is our question. Let's solve it for Q outer. So Q on the outer surface equals Q total minus Q inner. Okay, so now we just need to plug numbers. Total amount of charge is given, minus 50 nanocoulombs. Then minus from the expression which we got, and the amount of charge on the inner surface we just found. So two minuses, minus from the expression, minus from the charge. Don't forget about those minuses. So we will get minus 50 plus 100, so we will get plus 50 nanocoulombs. You see, it's not a rocket science, right? So you see that comparison with two-room situation, it's exactly what we have here. Charges cannot be inside of the material, they can be only on the inner surface or outer surface. And we know the total amount of charge that we provided